All right, hopefully that last video made sense to you. It's a little bit tricky when you're starting to get into it, looking at all those different ways of saying basically the same information, but hopefully that's starting to click. We're going to start to move into something different today and next. It's called Hess's Law. So let me see if I can describe Hess's Law to you. So in your notes it says, it talks about the guy who came up with this and why it came about. And a lot of it has to do with the fact that calorimetry is not always practical. So for example, let's say I want to know how much energy is in dynamite. Well, you don't want to throw dynamite in a calorimeter. That's called a bomb. Don't do that. So there's other ways we can figure out chemical reactions like that without actually having to do the experiment out, and that's where Hess's Law comes in. This is a theoretical, mathematical calculation that you rather than do the actual experiment. And it's built on this idea right here. That, let's say, let me use this example. So here's Cardston, here's Grath, Welling, Lethbridge. Let's say I want to know a certain distance here, but all I really know is the distance from Cardston to Welling, and maybe I know the distance from McGrath to Lethbridge. I know the distance from Welling to McGrath. Even though I don't know the distance from Cardston to Lethbridge, I have enough information here I could figure it out. Because I can take this piece, I can take this piece and that piece, and now I've got it figured out. Hess's Law is basically the same thing. If you've got a chemical A, and I know through whether it's calorimetry or some other experiment, I know how A turns into B, and I know B turns into C. I know those enthalpies, right? Delta H. This has its delta H. And I know that C can turn into D, has its delta H. Well, if I take those delta H's and combine them, it's basically the same as saying I went from here to here, and I can figure out that delta. So it's using known reactions to figure out our unknown reaction. And if I was you, I would draw this in that little space next to B, 1B there in your note. Okay, so let's go ahead and look at part 2 here and actually show you how this is done. So delta H can be determined by adding equations. We talked about that. Here's our steps. Number 1, start with a balanced desired equation. You have to know where you're trying to get to. Otherwise, you're not going to end up there, most likely. So, and it has to be balanced. Always start with a balanced equation. 2, then you're going to manipulate the known equations kind of like puzzle pieces to build the desired reaction. You can multiply them if you need double of something. You can reverse it if it was on the reactant side and you need it on the product side. You can do whatever you want. The trick is, whatever you do to the reaction, you also have to do. If I double the reaction, I double the delta. If I reverse the reaction, I have to flip the charge. If it was endothermic, now it's exo. And then if I get everything built the way I want, I can combine it and together. So let's try example number 1 here. What's the molar enthalpy for the formation of carbon monoxide? Remember that formation means making it from its elements. So I'm making carbon monoxide, which is just CO. And the elements are carbon and oxygen, but oxygen is diatomic. So to balance this, I have to do. Okay? So this is my desired equation. That's what I want to build. Now I don't know the delta H. That's what we're trying to find. So in your notes, take a look at those two in the reference table there. And I'm going to go through this one piece at a time and figure it out. So the first thing in my desired equation is carbon. I need 2 carbons on the reactants. So if I look at my reference table, reaction A has carbon, and it's already on the reactant side. It's just not the right number. So I'm going to say A times 2. So that gives me carbon plus 2O2 makes Now just to show you what I'm doing here, I'm now going to check that off because I have 2 carbons. I'm not going to check off oxygen yet because I have too many. And I don't have carbon monoxide, I have carbon dioxide. So I'll leave those. But because I doubled reaction A, remember I have to double its delta H. So now that's going to be a delta H of 7? Better double check that. Hold on. Don't trust my brain. Boom. Boom. All right. And it was a negative number, so I got to leave that negative in there. With these calculations, you have to put the positive or negative or it's... All right. Now, I move on to the next thing, and the next one in my equation is oxygen. But if you look, reaction A and reaction B both have oxygen. So I don't know which one to choose. So I'm going to skip this for now. I'll come back to it, but I'm going to skip it for now. I'm now going to go to carbon monoxide. And the only reaction with carbon monoxide is reaction. So I need 2 carbon monoxide. That's exactly what I have. But in the reference table, they're on the wrong side. So I have to reverse reaction. I'm going to write the whole thing backwards. 2 CO2s. They're becoming O's plus an O. And I have to also flip that delta H. So now that's a positive 566. All right, so let's do what we did before. Check off 2 carbon monoxides because boom, there they are. And you'll also notice something else has happened. I have 2 carbon dioxides on the reactant side. I have 2 carbon dioxides on the product side. So these are going to cancel each other out. They're gone. And with the oxygen, something similar, except I have 2 on the reactant side and 1 on the product side. So this one fully cancels. This is going to cancel down to a 1 instead of 2. So if you look, now I have 2 carbons, 1 oxygen, and my 2 carbon monoxides. I've built the desired equation. Carbons left, oxygen. So that matches exactly what I was trying to build. So since this worked, now what I do is I add those delta H together. So I take the negative 787, add 566. That gives me a delta H of negative 21. I should have 0.0. Now be a little bit careful when you're reading the question. Look back. The question says, what is the molar enthalpy? This is not molar enthalpy right here. That's delta H. That's total enthalpy. If I want molar enthalpy, I've got to divide it by the number of moles. If I take 221.0 kilojoules, divide it by moles of carbon monoxide, gives me 110.5 kilojoules. And there's my final answer. So it's just taking these pieces and putting them together just like a puzzle, making sure in the end you have all the things you want and you don't have anything left over. Sometimes you're going to have leftovers you're going to do. So I'm going to stop this one for now. Then we're going to go through the other 2 examples in the next video. Then you should be set up to try these on your own. Check out the examples in the next one.